All right, so here we are. We have 5 points that we need to. So each of the first, I think it's first 2 questions. Let me see here. Yes, the first 2 questions are pretty involved. I'm going to do one for you. I'm going to do this first one here, and the second one will be exactly the same procedure. And then the remaining 11 questions will all be conceptual, so those will go fairly quickly, but I do want to take the time to discuss each one as we go through it. They're all little variations on the same idea, which involves the second derivative test, and that builds on the first derivative test. Okay, so the function that we have here is h of x equals x cubed minus 12x. And the first thing that we have to find are the critical points. They want the points. Remember, a critical value is the x value. When they ask for the critical points, they actually want the ordered pair. Okay, and then we have to classify each point as a relative maximum or a relative minimum or neither. So that's part A. So the first thing, since we're going to be using the first and second derivative tests, I'm just going to go ahead and find the derivatives. That the first one is going to be applying the power rule to this. 3 comes out front, x squared, subtracting 1 from the exponent, and then the derivative of this linear component is just minus 12. Okay, and then taking the second derivative, we have 2 times 3, that's 6x, and the derivative of a constant is 0. So now we found, we have the function, the first derivative, and the second derivative. So moving on to part A, remember we're finding the critical points. The critical points are found by setting the first derivative equal to 0. And solving for x. So in doing that, we have, here's the first derivative, 3x squared minus 12 is equal to 0. And so when we add 12 to both sides, we can isolate our x term. And so then we get 3x squared is equal to 12. And now we're going to divide both sides by 3. And we get x squared equals 4. Now we can apply the square root property. That means that if we have a square equal to a value, we can take the square root of both sides of the equation. And what we get then, solving this, we get x equals, and remember it produces 2 values. When you take 2 values, when you take the square root of x squared, you get 2 values. You get the plus and you get the minus of the square root of 4. So that's 2, plus or minus 2. These are our critical values. Now, whenever you are looking for an ordered pair and you want to calculate the y value that goes with an x value, you're going to use your original function. So we are going to calculate our function h of 2 is 2 cubed minus 12 times 2. Okay, we're just substituting 2 into our original function. And we get 8 minus 24, and that's going to be negative 16. Then we do the same thing for minus 2. So we have minus 2 cubed minus 12 times minus 2, and this is going to be negative 8, right? Because when you cube a negative number, it's still negative. So it's going to be negative 8. Then we have a double negative here, so it's going to be plus 24. And that gives me 16. All right, so from this information now, we know then that the critical points right now we're talking about points are 2, negative 16, and negative 2, 16. These are the critical points. Plus or minus 2 are the critical values. That's the location of the critical points. And remember, critical values are x values, and then to find the actual points, you need ordered pairs, and that's why we plugged in these numbers to get the y values that go with it, okay? Now, one thing that I've experienced is students often get confused about which function they're using, okay? So the first function is always used to find the y values of the points on the curve of the function. The first derivative is used to find the critical values, and the second derivative is used to find inflection points to determine concavity, all right? We're not finished with part A yet. We found the critical points, and now we need to decide, are these locations of relative maximums, minimums, or neither? Okay, that was the second part of part A. So that's what I'm going to do now. I'm going to use, in order to determine if something is a maximum or minimum, all I need to know is it concave up or concave down? So if it's concave down, there's a maximum there. And if it's concave up, there's a minimum. So we're going to use the second derivative. Okay, so the first point that we're going to plug in is the 2. I meant to put a 2 there, not an x. Okay, the second derivative evaluated at 2 is 6 times 2. Since this is positive, we know that it's concave up like this, okay? A positive second derivative means it's concave up. That means this is a minimum. So okay, so the minimum value is negative 16. The where does it occur is at 2. Remember, x values give you a location, right? The location. The y values give you the what. What is occurring at 2? There's a minimum of negative 16. See how that works? Remember, x values are where, y values are what. So let me just make a little note. Okay, just remind yourself that. It will really help you keep things straight in your mind, because often people get the X and Y values interchanged and they get confused. Just tell yourself, X values show me where something is happening. Y values show me what is happening. So we have a minimum of -16 at 2. Okay. Now, we want to plug in the other critical value. See here, it's negative. So negative implies there is a relative maximum, right? Because when you get the second derivative being negative, your curve is concave down at that point, and so you're going to have a maximum. Oops, I meant to say of 16 at, where are we, -2? Yeah, we're plugging in -2. So since we got a negative answer, we know that it's concave up. I'm sorry, concave down for negative. Here we got a positive, so it was concave up. So we have a relative maximum of 16 at -2. Okay, any questions so far? This is all that we've done for part A, just part A. So you can see how involved these problems are, and I've used almost a full page. Okay, I just have a little bit left at the bottom. So you can see that these problems are really involved, and that's why there are only 2 questions for this homework assignment. So once we get through this first one, you'll see that the rest of the homework assignment is fine. Okay. All righty. So we finished part A. Now let's go back to the problem and see what part B is asking us. So part B says, identify intervals where the function is increasing or decreasing. This question is always answered by the first derivative test. So that's what we're going to use now. And I'm going to go ahead and write that out on the okay. I want you to pay attention here to some keywords. Locate, where, okay? Those are keywords telling you your answer, you're going to be looking at the x-axis. If you're trying to find where, or if you're locating where something happens, you are looking at the x-axis, okay? So if you will recall, our original function h of x is, let me just write that down up here, x cubed minus 12x. And then, of course, whenever you're trying to find increasing or decreasing, you're looking at the first derivative, okay? So I'm going to put that in parentheses here. First derivative test. Okay? So taking the derivative here, I have 3x squared minus 12. We did that earlier. This is what I want to focus on. I'm going to now look for, let's see, we found the critical values, right? And we found the critical values to be at -2 and 2. And remember, I'm working with the x-axis here because I'm trying to find where our function is increasing or decreasing. So I'm going to use my first derivative, and I've got 3 intervals here. Now it's important to note that for each, because these are critical points, and these are the only places where the first derivative is 0, then in each interval, the first derivative is going to be all positive or all negative, because there's no changing where it crosses the x-axis. So it's either all positive or all negative. So I only need 1 point. If I can find what the sign of the first derivative from 1 point, I know the sign for all the points in that interval. So it doesn't matter what point I pick because I'm just looking at the sign, either positive or negative, okay? So here I'm going to pick -3. I always like to pick 0 because it's easy to calculate. So that's between -2 and 2. And over here, I'll pick 3. Okay, so these are my test points. Because I'm doing the first derivative test, I'm going to use the first derivative. So f prime of -3 is equal to 3 times -3 squared minus 12. Okay, I'm using the first derivative, and I'm just plugging -3 in for x. And then I calculate that. I have -3 squared, that's 9, times 3 is 27. 27 minus 12 is 15. All right, this is positive. And since we're doing the first derivative, positive implies it's increasing. Okay, so we're going to write on this interval increasing. Next interval, we're going to take our 0 value, and we get 3 times 0 minus 12. That's negative, so it's decreasing. And then finally, we're going to do our last point from the third interval. And we have 27 minus 12, which is 15. So it's positive. So it's increasing. And I'm just going to write those in on my interval to show where. So to answer the question where our function is increasing, the function, and I used f and I should have used h. I'm sorry, that was a mistake. I'm so used to using f, I just forgot. This is h here. This is h. There we go. You probably noticed that. But anyway, okay. So the function h is increasing on the intervals from minus infinity, right? This is minus infinity. This is positive infinity. So you just read from left to right, minus infinity to minus 2. And then also from 2 to infinity. I used a comma here. Normally I would use a U because that stands for union. You're joining the two sets together, but I think in your homework it uses a comma. So this is the format they wanted in. And finally, we see that it's decreasing from between -2 and 2. So this is how you would answer the question for part B. All right. All right, let's go back to the homework assignment. And now we're on to part C. Part C says, give the coordinates of any inflection points. Okay, so when you're looking for an inflection point, you set the second derivative equal to 0. Wait a minute, let me go back to that for a second. I want to make sure I got all of that. If there was anything else. Yeah, just the inflection points. That's all we're looking for. Okay, so part C. Let me switch to my pen. Okay, so okay. So the second derivative, remember, we got 6x for the second derivative, right? So we're going to set this equal to 0. And then if you divide both sides by 6, you see that x is equal to 0. So this is the location. This is the location of the inflection point. All right. Now, just like we did for the first derivative test, we plot the inflection point. And then we have now, because we had one inflection point, we have 2 intervals that have been created by that one inflection point. And so we're going to pick a point from each interval. And so I'm going to pick -1 on this side and +1 on this side. And we plug those into the second derivative. And we get 6 times -1 is -6. The fact that it's negative and the fact that we're using the second derivative shows that it's concave down. So this interval, our function is concave down. By the way, I kind of, I moved on to the next point. I'm just so used to doing that. I think this actually is starting to answer part D. And I didn't quite find the inflection point, so I'm getting ahead of myself. So let me just go back here and just say that to find the point, you got to find the y value. And remember that h of 0 is equal to, so now we got to go back to the original function. And the original function, right here, if I plug in 0, h of 0 is 0, right? So we get 0 cubed minus 12 times 0 equals 0. So the inflection point is 0, 0. Okay, I just forgot that little part there. And I think that was all we had to do for part C, was find the inflection point. We did right here, 0, 0, that's the origin, is the inflection point. And now with part D, I'm pretty sure they're going to ask us what is the concavity. So I can't remember for sure, but I'm almost positive that's what they're asking. So I plug in now the other test point. Since it's positive, our function is concave down on that interval. I mean, concave up. Concave up. Positive is up, negative is down. Okay. Now let's go back to the homework and see, and before I do that, I'll just write it out for you. H of x is concave up on this interval from -infinity to 0, and concave down on 0 to infinity. There we have it. So when you're asking where is the function concave up and where is it down, remember you're giving the values that come from the x-axis. So these intervals represent intervals of x values on the x-axis, right? So your answer to where is always the x-axis. I just can't emphasize that enough. Okay, so here we go. Back to the homework. Let's see what we still have to answer. Okay, so it says identify the intervals where the function is concave up or concave down. That was part D. Now we have to sketch the graph. You can sketch the graph based on all of this information. So let me just do that on the next page of my notes here. Now you're not going to have to sketch a graph, right? Because you're taking a multiple choice test, or you're just going to have to select the graph. So basically all you have to know is kind of the general behavior. And if you're using a graphing calculator, you can have your calculator sketch it for you, or you can do it in Desmos. And in fact, why don't we just do that rather than, I mean, my drawing is not going to be very helpful. So let's go to Desmos and sketch this graph. To find the cube, you just go here, select this button, and then you type a 3 in. And that gives you your cube. And then we subtract 12x. And there's our function, okay? So notice that it's concave up on the interval, everything to the left of the y-axis. Remember, here's an inflection point. Okay, 0, 0, that's the origin. That's the inflection point. That's where the concavity changes from, it's on the left, it's concave down, right? Because on the left side of the y-axis here, it looks kind of like a frown. It's concave down. And then on the right side, you can see it changes to concave up. It's more like a smile. So this is the inflection point where the concavity changes. And remember, that comes from the second derivative test, is how we determine that. Now, if you're talking about increasing or decreasing, notice here at this point, this was a critical value. That is where the derivative is 0. What is the derivative? The derivative is the slope of the tangent. And if I draw a tangent line there, it's going to be a horizontal line at that peak, okay? That's the tangent line, is horizontal line here. On the left of that point right here at the critical point, the function is going up as we move from left to right. Then at this point, suddenly on the next interval, on the other side of -2, it starts going down. And it keeps going down until we get to the other critical value, which was 2, remember. And now it changes to increasing and it's going up again. So that comes from the first derivative test. So there you have it. This is a pretty good, Desmos is very helpful to answer these questions. And in fact, you can answer these questions just by looking at the graph and hovering over the points. No, I'm not. Okay, here we go. All right, you should be able to see that now. All righty, so the first, it says sketch the graph that possesses the characteristics listed. So the first characteristic is that it's concave down at 1, 5. and it's concave up at 7, -3. So, but I said, remember, start with the first. So 1, 5. So I'm going to look at this graph, and I'm going to find 1, 5. Here, x equals 1, y equals 5. This point, where my cursor is, or my arrow, is not even on the curve. So we can just eliminate the first choice right off the bat. The point has to exist on the curve. If you want to say the function is concave down at a certain point, it's got to be on the curve, right? That one isn't. So we can eliminate A. Now going to B. We want to see if it's concave down at 1, 5. Here also 1, 5. This point is not on the curve, so we can eliminate B. Going to C, we can go to 1 and then 5. Yes, that point is on the curve. And we want to know, is it concave up, or I'm sorry, concave down at this point? Yes, it is concave down. It looks at this point, the curve is bending down. So it is concave down at this point. Okay, so this is a possible choice. Now we go to part D and check. We have to go to the point 1, 5. Notice this is not on the graph, so we've eliminated this one. So it turns out that I don't even have to check these other characteristics here. This is the correct choice, C is. But before I go on, let me just show you how these two characteristics are shown here. All right. So the first one says concave up at 7, -3. By the way, can you see my graph? Hold on, I just realized. Yeah, you can, good. Sometimes, or I had this experience where I pulled a pop-up and it wasn't showing the pop-up, but it looks like from what I can see that you can see that. That's good. Okay. So here we're looking at concave up at 7, -3. Now we're going to go out to 7, -3. 1, 2, 3, 4, 5, 6, 7. Down 1, 2, 3. It's concave up there. You can see how it's bending up. And the final characteristic is that it has an inflection point at 4, 1. Let's see what that looks like. We know this is the correct choice. So 1, 2, 3, 4, and at 1, yes, it looks like that is an inflection point. In other words, to the left of that point, it's concave down, and to the right of that point, it's concave up. So yes, we do have an inflection point there. It changes, the concavity changes as you pass through that point, okay? So moving on to the next one. It says, for the graph shown, identify the points of inflection and the intervals where the function is concave up or concave down. Now this is kind of the reverse of the previous problem. In problem number 3, we were looking at the characteristics and trying to pick out the graph. Now we were looking at the graph and trying to show what the characteristics are. So it's the reverse. So pulling this up, and I'm just going to check. Looks like you can see it okay. We're looking at, first we want to find the points of inflection. Well, if we go here, you can see the curve. Let me just follow the curve. It is concave up. And then right at this point here, it changes to concave down. So this point is the point of inflection. And the coordinates of that point, as you can see, are 1, 2. So I'm going to type in here 1, 2. Now it says identify the intervals where the function is concave up or concave down. So the inflection point is kind of the dividing point. And remember, when we're looking for intervals, it says, look at part B. Let me go back to part B here. Look at this key word here, where. that keyword tells you, look at the x-axis. So when I identify this point, this is where the concavity changes, but I'm not concerned about the 2, right? That's the y value. I'm concerned about the x value. So I'm going to bring it down here to the x-axis, and we are at x equal 1. To the left is the function is concave up. To the right, the function is concave down. And what are those two intervals? Well, on the left-hand side, it's minus infinity to 1. And then on the right-hand side, it's 1 to infinity. So going back to the answers, the function is concave up on minus infinity to 1. And the function is concave down on 1 to infinity. Okay? All right, next question. Sketch a graph that possesses the characteristics listed below, and it gives us 2 characteristics, and again, it gives us 4 choices. The best way to do these problems where you're trying to pick a graph is to start with the first characteristic and eliminate the ones that don't match that characteristic, then go on to the second characteristic. So the first characteristic says that f is increasing and concave up on the interval from minus infinity to 1. Where is it increasing? On this interval. So that's an x-axis that I'm looking at. So I go to my the first choice here, and I find 1 is right here, and it says f is increasing. Well, obviously this function is decreasing as we go from left to right. So this is not going to work. Going to the next picture. Yes, this function is increasing, but you'll notice, and I'm just going to go ahead and look at this, concave down from 1 to infinity, and that is on the right-hand side, 1 to infinity. Here's 1, and then if you go off to infinity, you're going this way. It's concave up, not concave down. So I can go ahead and eliminate that one. I'm kind of breaking out of my rule that I said, but that you can do that too. You don't have to be locked in to anything in particular. But anyway, so this looks like this is the choice, but let's go ahead and look at this one. This one violates 1 here because this one also is decreasing. Watch, as I go from left to right, I'm going down, right? So that's decreasing. So that one's out. And this one is in, but it fails the second point because it says it's concave down on 1 to, oh wait, no, wait, I'm getting backwards now. No, on 1 to infinity, this is concave down because it looks like a frown, right? So this is the correct choice. I don't know what I was saying about this one over here. Let me go back over here. I think I got it backwards. This one, from 1 to infinity, it's concave up. So it is not going to work. Because remember, here it says f is increasing and concave down on 1 to infinity. So this is the one where everywhere it's increasing, 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 increasing on both intervals. But then here from 1 to infinity, see the shape is kind of bending down. It's more like a frown than a smile. So that is the correct choice. Please stop me if you have any questions. I hope I'm not going through this too fast. Okay, wow, look at that list of characteristics that they're giving us. Woo, that's a long one. All right, I'm guessing that we'll be able to find the correct choice before we get through that entire list. There are 1, 2, 3, 4, 5, 6, 7, 8 characteristics that we have to check. I'm guessing we'll be able to find the correct one before we get, to the 8th. Okay, start with A. We want to find where the first, we want the first derivative at -2 to equal 0. So at -2, I'm sorry, -2 is right here, okay, where I'm pointing my arrow. That's -2 on the x-axis. That is telling me that the derivative should be 0 there. Well, obviously the derivative is not 0, because if I go to the curve and I draw a tangent line, it's certainly not a horizontal line. The tangent is going to be positive, to have a positive slope, right? I'm kind of making the motion there for where the tangent is going to be. The only place that the tangent is 0 on this curve is right here at this bottom point. The tangent has 0 slope. The derivative is 0 at this point, and that is not at -2. So this graph is out. It fails the very first characteristic. Moving on to the second graph, at -2, yes, the derivative is 0. See how we have a maximum there? And the derivative is 0 only at a relative maximum or a relative minimum. So this is a relative maximum. So the first characteristic is satisfied by this graph. So we can't eliminate this one yet. Going on to the next one. Here is -2. And that is not a relative maximum. Here's the maximum. So the first derivative is 0 at -1, not at -2. So the first characteristic, this one's out. C is out. Now, going on to this one here. Yes, at -2, the derivative is 0, because here at this is a relative minimum, and that's where the derivative is going to be 0, either at a max or a minimum. The derivative is 0 also here. Okay, so at -2 and it looks like -6, there's a derivative of being 0. See right here? This graph also satisfies this one right here. We just showed the derivative, first derivative at -6 is 0 because there was a relative maximum there. So D is looking pretty good right now. The other one was B. Let's see if we can, so we've eliminated A and C, and now we've got to see if we can eliminate B somewhere. So let's go through this list and see where we can eliminate B. Here, the second derivative at -2 is less than 0. That means it's concave down because we're looking at the second derivative. Less than 0 means it's negative. A negative second derivative means it's concave down. But you can see here at -2, yes, the graph is concave down. It looks like a frown, right? So the second characteristic is satisfied by this graph. How about this one here? F of -2 equals 2. Let's check both of these two choices that are still in the running. F of -2, here's -2. Yes, F of -2 equals 2 because it's the height here that this point has a y-coordinate of 2. That's the output of the function. So yes, F of -2 is equal to 2. Now let's go back to D. Here, F of -2 equals -2. So D fails this characteristic. So I've only gone through 3 characteristics. I've already eliminated D, and now we know therefore B has to be the correct choice. And so I didn't even have to go through the whole list. Okay? All right. Here, this question. Determine which graph is the derivative of the other and explain why. Okay, let's read what they're getting at here. It says the function g is the derivative of the function h because g equals 0 at all the values of x where h has a relative minimum or maximum. So remember, the derivative, if it's equal to 0 at a certain point, then there's a relative maximum or minimum at that point. And we've got to compare these two curves and look at them, okay? So here you can see the red curve has a relative maximum right there, And notice that the blue curve is equal to 0 at that point. Then this one, it doesn't have a relative or maximum, but you can see the tangent is horizontal because it's flattened out there. So the tangent has a slope of 0, and that's exactly what the derivative is showing here. It's 0 right there at that point. Then over here, it has a minimum value, and notice the blue curve is 0 at that point. So based on what I'm looking at, the blue curve is the derivative, and the red curve is the actual function that g is the derivative of h. That's what I'm seeing here. So let's go back to our choices. And actually, that's exactly what this says. The function g is the derivative of the function h because g equals 0 at all the values of x where h has a relative minimum or maximum. So the choice is obviously A. I didn't even have to read the other choices. Okay. This one says, use calculus to prove that the relative minimum or maximum for any function f, as shown below, occurs at x equal minus b over 2a. Now, you'll notice there's only one value, and that's because the function, now this isn't for any function, this is for all functions that are in this format where ax squared plus bx plus c is your f. That's a quadratic function. So when it says for any function f, they mean for any quadratic function. That's what they're saying right there, because this is the format that the function has to be in, and this is a quadratic function. So basically, remember this formula from algebra? This is the vertex formula. Whenever you wanted to find the vertex of a parabola, you use this formula. And that's because the vertex is where the relative minimum or maximum occurs. The vertex is a critical point. We never talked like that when we did algebra because we weren't studying calculus. But when you're studying calculus, you think like that. You're thinking in terms of the first derivative. So let's go ahead and do this problem. I'm going to show you how. So here we have our quadratic function. We don't know what a, b, and c are, but it doesn't matter. We take the first derivative. And you take your power, multiply it by your constant in front. And here is the linear piece. So the derivative is the slope, which is b. Here's my first derivative. Now I'm going to set it equal to 0 and solve for x. To isolate x, I subtract b from both sides, and I get that 2ax equals minus b. And then to isolate the x again, now we divide by 2a.
I didn't understand that.
My phone is talking to me. Sorry. I don't know. Just out of the blue, it decided to do that. All right. You probably didn't understand that either, huh? Just kind of... Anyway, never mind. No, you did. You're smarter than Bixby. Okay. All right, so there we show that the vertex formula is also giving you the critical value. So if you have a parabola, you've got a high point there, and here you have a low point. These are the critical values, or the critical points, I should say, and those are also the vertexes for a parabola. And so that's our equation to find the critical point for quadratic. Okay, now, let's see here. Where will the relative minimum or maximum for the function occur? Of course, not at an inflection point. An inflection point is for concavity. Critical value is where you have relative maximum or minimum. So there you go. Then it says determine the derivative of the function. I guess I went through these steps on the paper, so I'll let you do those on your own. And here we have the graph of a function f of x is shown, and assume f is twice differentiable. That just means that it has a first derivative and also a second derivative. And it says at x equal 2, the graph of f increases, right? Here's 2, and as we go from left to right, it is increasing the whole way. So it increases at 2 also. So it increases. And then notice that it's bending down, so that is concave down, okay? Which is the smallest of these values here? Okay, well, what is f of 2? Here you can see that f of 2 is 0, right? Because it's on the x-axis and the y value is 0 when x equals 2. So this is 0. The derivative, notice the derivative is positive because the function is increasing at 2. And the second derivative is negative because the function is concave down at 2. So which of these is the smallest? Well, it's the negative one, right? And the negative one is the second derivative because of the concave being down. The graph of f of x is shown on the interval. Notice this is a linear function. It says determine whether each is less than, greater than, or equal to 0, and assume f is twice differentiable. Well, because this is a linear function, when you take the first derivative, you're going to get a constant, right? And what is that constant? Well, it's the slope of the line. The first derivative is the slope of the line. The slope is obviously negative because see how the line is going down, it's decreasing, and it's slanted this way, so it's a negative slope. So the first derivative is less than 0. Now, what about the function itself? Notice that the function itself is above the x-axis. That means all the y values are positive. So the y values, which are the function values, are positive. So I say f of x is greater than 0. And finally, the first derivative is a constant because it's a linear function. And that means that if you take the second derivative, you know, you're differentiating the first derivative, that's the second derivative, it's going to be 0, right? Because we have a linear function. So we put the equal sign there. So that's how you do that problem. You're just, see how conceptual this is? It's really understanding what it means for the, you know, the first derivative. What does it mean the second derivative? That's why I wanted to walk through you with this, or through this with you. Can't talk today. Okay. So the graph of a company's profit, P of T in dollars, is given by this curve here, and the x-axis is in time. Those are in months. So we have 7 months, 14 months, 21 months, etc. There are 8 parts A and B. Estimate to the nearest whole numbers labeled on the horizontal axis any values of t where the second derivative is 0. That would be an inflection point, right? When the second derivative is 0, that's an inflection point. That's where concavity changes. So let's just look at this curve. We're coming along here. Notice it's concave down. And then at this point, suddenly it changes to concave up. So this right here is an inflection point. They just want the values on the horizontal axis. So I go down to the horizontal axis. I see that that's at 14. So I'm going to type in 14 here. Then I'm going to continue. Now it's concave up. And then notice here it's concave down. So it changes right at about here. And that on the x-axis is 28. So I'm going to type in 28 as well. And then moving right along, it's concave down, and then here it's concave up. So there's a change there, and it changes right at about this point. So if I go to the t-axis, it's at 49. So there you have it. All right, now we're going to list any values of t where the second derivative is the same as the first derivative. All righty. Well, the second derivative is, again, having to do with concavity. So we want, and the first derivative has to do with increasing or decreasing. So we're really looking at the sign because we can't calculate the first derivative or the second derivative. We're just looking at the sign. So let's go along the curve here. The second derivative is, this is concave down. So the second derivative is negative. And the first derivative here is positive because it's increasing. So all along this piece, the first derivative is positive and the second derivative is negative. So there's no point on that curve that I'm going to include, right? Where the first and second derivative are the same because one is positive, one is negative. Now here, notice that the tangent line at this point that I'm pointing to right now is horizontal. The tangent line is horizontal. That means the derivative, the first derivative is 0. But this also, as we showed in part A, happens to be an inflection point. So the second derivative is 0 there also. So in this case, the second derivative and the first derivative are both 0. So I can, now the question is where? See that keyword there? Where? So I want my values to be on the x-axis. So at this point, I'm at 14. So I'm entering in 14. And I said x-axis, I meant t-axis. The horizontal axis is what I'm talking about there. Okay. Now we are concave up and it's increasing, but I can't be for sure that the values are actually the same there. There's an inflection point here. So that would be the derivative being 0. Or the second derivative, I'm sorry, the second derivative being 0. But again, I can't calculate the derivatives, so I don't know if they're the same. That's a little ambiguous there. But if I go up here, I have a tangent, a horizontal tangent, so I know the first derivative is 0, but I know the second derivative is not because it's negative, because it's concave down. And then here it's decreasing. So I don't know. I'm not exactly sure what they're trying to get at. I'm thinking that 14 is the only correct answer, but I could be wrong. But I'm just going to check my answer and see. I might be wrong if I'm not. Nope, that's right. Okay. All right. The graph of a company's profit, P of T in dollars at month T is shown. And we want to complete parts A through E. So there are 5 parts here. So there's a lot to this actual problem here. So here we go. We're looking at when is the first derivative greater than 0. So that means it's positive. And here we're looking at the second derivative equal to 0. So that means it's an inflection point. So we're only going to be looking at the inflection points. Okay. Here's an inflection point because it's concave up on the left and concave down on the right. So there's an inflection point at 18. In other words, the second derivative is 0. However, notice that at this point, the tangent is going to be horizontal because there's a flattening there of the curve. So the first derivative is 0, not positive. So that one's out. Now we go to the next inflection point, which is right here at 36, because here it's concave up, and then here it's concave down. And we can see there, because the function is decreasing, the first derivative is negative, so that's still, it's got to be positive, right? And then now here the first derivative is 0, that this is out. Here's an inflection point because here it's concave up, then it's concave down. So this at 63 is an inflection point. And notice the derivative there is positive because it's increasing. The function is increasing. So 63 is the answer. And after 63, there are no other inflection points. So this is the only answer that we have. Part B. Now we're looking at where is the derivative less than 0. That is when the function is decreasing. And then we also want to find when is it decreasing, but also having an inflection point. So here the function is decreasing, here it's increasing, and here it's decreasing. You can see on this piece right here where it's decreasing, there are no inflection points. It's just concave down everywhere there. The inflection point here, the function is increasing, and we want to know when is it decreasing, so that's out. Notice here, the function is, the first derivative is 0. So this point is out. This is an inflection point, but the first derivative is 0. So this one's out. The other inflection point is right, where did we say? Right here, 36. And you can see that, yes, it's decreasing there. So we have both the second derivative equals 0 because it's an inflection point, and because it's decreasing, the first derivative is less than 0. So this is the point that we're looking for, 36. And notice we're looking on the horizontal axis because the question is where is this taking place? So it's 36. Okay. And I think that's the only one that I can see. Yes. Now we're looking for when is the first derivative 0 and the second derivative is greater than 0. When the second derivative is positive, that means concave up. And we're also looking at when the first derivative is 0, that's when you have a relative maximum or minimum. So, but because this is positive, it's concave up, that means you can't have a maximum, it has to be a minimum because it's shaped like a valley, right? And you've got a bottom point if it's concave up. So right here, here we have the first derivative being 0, but that's an inflection point, and we want the second derivative to be greater than 0. So down here is the only relative minimum on the entire graph. So it's at 54 is our answer for that one. I hope you guys are following me with these because I feel like I'm burning through this really fast, but please feel free to interrupt me if you have a question. All right, part D. Now we've got, again, we have a tangent that's horizontal because the first derivative is 0. And because this is negative, we're looking for, it's concave up, concave down, which means we're looking for a relative maximum. And the only maximum that I can see, the relative maximum, is right here at 72. Here we're looking for a flattening of the curve because we have a horizontal tangent because the first derivative is 0, but we're also looking for an inflection point. And this is an inflection point because on the left it's concave up and on the right it's concave down. And it's also a flattening of the curve, so it has a horizontal tangent and the first derivative is 0. So this spot is the only spot like that, that's at 18. So it looks to me like when you do this problem, all the answers for this particular problem, they're only one choice. Okay. And finally, the very last problem, we want to find on the interval shown for which graph are both f prime and f double prime. In other words, the first and second derivative, where are they positive? Well, the first derivative being positive means that we have an increasing function. These two functions are decreasing, and this one is constant. So C and E are the only ones with a positive first derivative. C has a negative second derivative because it's concave down, and D has a positive second derivative because it's concave up, so E is the correct choice. And there you have it. So I hope this helps you with your homework. The questions aren't going to be exactly the same necessarily, but I hope that I've kind of shed some light on this whole first and second derivative